In the realm of elite performance, the line between a gold medal and a catastrophic injury is measured in millimeters and milliseconds. Welcome to the modern gymnastics arena. To the uninitiated, it looks like a playground, but to the engineer, it is a high-precision ecosystem of safety technology. This is where physics meets physiology, designed to catch the human body falling from the heavens. The foundation of all acrobatics is the spring floor. It is not merely carpet over wood, it is a kinetic battery. A sandwich of birch plywood and thousands of steel coils works to absorb impact and return kinetic energy, launching athletes into the stratosphere. But what goes up must come down. The landing zones are governed by the 20-centimeter competition standard, mats designed for calculated impact displacement. In training, we go deeper. The foam pit, filled with thousands of loose polyurethane cubes, utilizes loose body physics to create fluid-like deceleration. Beside it lies the Resolite pit, a solid foam transition that bridges the gap between total immersion and the firmness of the podium. And for the final layer of defense, the Sting mat, a thin, high-density savior thrown in at the last second to dissipate the shockwave of a questionable landing. The apparatus themselves have evolved from rigid iron to dynamic composites. The vault table, once a narrow horse, is now a broad platform fortified by the safety collar. Often called the horseshoe or the donut, this U-shaped padding surrounds the springboard, physically preventing the athlete from striking the metal base during a high-velocity entry. On the uneven bars, safety is woven into the very fiber of the rails. Fiberglass cores wrapped in wood veneer offer tension and flex technology, preventing the bar from snapping under G-force loads. Even the balance beam is an engineering marvel. Its surface is no longer polished wood, but a synthetic suede cushioned with padding, providing the friction necessary for traction while mitigating the brutality of a fall. From the low-profile training beams to the foam mushroom trainers, every edge is softened, every surface engineered for forgiveness. But how do humans learn to fly before they can land? The answer lies in overhead suspension. The spotting rig and bungee system allow athletes to defy gravity repeatedly without consequence. Central to this is the rotational twisting belt. A complex bearing mechanism within the belt allows for free rotation on multiple axes while suspended. Whether it is a single hoop or a complex 3D gimbal, this technology permits the rehearsal of quadruple twists. When combined with high-density spotting blocks and the manual intervention of a coach, the learning curve is de-risked. Even the high bar utilizes safety loops, straps that lock the gymnast's wrists to the bar, ensuring they cannot fly off during the centrifugal violence of giant swings. Finally, we reach the interface between flesh and machine. The hands. Carbon fiber and leather grips equipped with dowels create a mechanical lock on the bar, reducing grip fatigue and preventing the skin from peeling off. Underneath, plastic inserts and wrist supports distribute massive torque away from the joint. And that ubiquitous white dust? Magnesium carbonate. It is not just chalk. It is a friction control agent, absorbing sweat to prevent the catastrophic slip. Coupled with the video replay delay system, which allows immediate visual feedback, the athlete is armored in both data and material. This arsenal of foam, fiberglass, and physics serves a singular purpose. It does not just protect, it propels. By removing the fear of the fall, we unlock the potential of the flight. In a world increasingly obsessed with safety, gymnastics teaches us a profound lesson. True security isn't about avoiding risk. It is about engineering a reality where we can survive the failures required to achieve the impossible. We build softer worlds so that humans can become harder, faster, and stronger.